Day 2 of learning AI ML and machine learning in few minutes concept wise. In previous video we had discussed about linear regression, and in today's video we will discuss about logistic regression. I will teach you the concept of artificial intelligence and machine learning, and in homework you will learn how to write code using AI, because today's era 90% of the code AI can write. Nowadays and in future, company requires what things? The clarity of your concept in artificial intelligence and machine learning to build a project. So without wasting time, let's start. In today's video, we will discuss about logistic regression, the architecture and mechanics of logistic regression. In linear regression, I have taught you that the output line are straight line, but in logistic regression, it converts into S-shaped line. The concept behind it, let's see. Linear logic shatters when predicting probabilities. Your linear regression on left hand side, we can see that linear regression provides or produces the outputs like minus 25, 4.7, 100, 1000. It implies that 150% chance of spam or a minus 20% chance of the disease, they are not realistic. So what we need binary outputs. Means if we are doing spam detection in email, then we want that when we give input to our model will provide that 1 means yes, email is spam, and 0 means no, email is not spam. So we need the probability, and linear regression cannot guarantee bounded probability. A new architecture is required. On the right hand side we can see the classification we required is we need probability between 0 to 1. For that, what should we need to do? In linear regression, we can have all range of output. We can have minus 200 plus 300. Means our range of output in linear regression is minus infinity to infinity, and we want to convert this output into probability. So we need a function which converts our output into 0 to 1. So here is a journey of invention of logistic regression is that in 1938 population dynamics, some scientists observed that population growth is not linear. It follows a biological cadence: slow, fast, saturate, then further many times it stays saturate, then again increases slow, then fast, then saturate. This create the foundational S curve, and after more than 100 years statistical probability, David Cox realized this logistic function perfectly solves the classification problem. It naturally and smoothly maps the linear scores directly into valid probability, and this function is none other than the sigmoid activation function, the muscle of logistic regression. Let's see the autonomy of logistic engine. The skeleton is which will which have the skeleton is which we already learn is linear regression. Y is equals to wx plus b here, z is equals to w transpose x plus b. This is the same thing. When we pass this output z into sigmoid activation function 1 upon 1 plus e raised to minus z, it converts or it maps this range in between 0 to 1. Means we get output between 0 to 1, continuous probability transition. The intuition is checked as we can see in the presentation. If z is equals to 0, sigmoid if z is equals to 10, we pass 10 into sigmoid activation function and we get 0.9995, which is almost yes. If we have z is equals to 0, sigmoid activation function give 0.5 as output, and maybe you can see if z is also minus 10, we get 0.0005, mean almost no. What is key takeaway of this sigmoid activation function? Why scientists use this sigmoid activation function? Because of researchers favor sigmoid because it creates a smooth transition from 0 to 1 rather than hard boundaries, making mathematical optimization possible. The geography of binary decision making. We can see the geographical perspective of binary decision making. First of all, what is the binary decision making? We have output either in 0 or 1, or 1 or yes or no. Yes means 1 and 0 means no. You can see in the graph also that fraud detection system is upper side, normal is lower side. Means if we get 1, then our new data point goes into the upper side of the line. If we get 0, then new data point goes into the lower side of the line. But when our value of z is 0, means output of linear regression is 0, we get sigma degradation function 0.5, means we have hard boundary, and this is the geometric limitation. This creates a linear decision boundary. The model requires a perfectly straight line to separate classes. It cannot draw circles, curves, or isolate clusters. This is the greatest physical limitation of logistic regression. Again, one of the most important thing about logistic regression is that the assumption that this algorithm makes very quietly is that the logistic regression assumes that the given parameters or given features are independent. Means sample must be independent. If same user appears 500 times, the model artificially inflates its confidence. Means that same user have 500 mails and all mails are normal, then user get confidence on this, then model get confidence on that user, and when this user provides another mail, however it is fraud, our model will predict this mail as a true or normal mail. This is the limit. This is the assumption of logistic regression. It assumes that provided data does not have any multi-collinearity, means feature cannot duplicate information. Weights become violent, unstable, and interpretation fails. Third assumption: sample size versus features. Logistic regression assumes that a dataset with 1000 features and 15 samples will simply memorize data. High data volume are strictly required. And fourth assumption is that class balance. If you give 99,000 normal spam and 1000 fraud spam, then your model always predict normal spam. In training, you can see 99% accuracy, you are happy, but in reality, this model fails because it does not provide a proper data. When you feed data to the logistic regression, it must contain some comparable amount of yes or no. Next thing, in linear regression, we are using mean squared error as a cost function, but we don't use mean square. We should not use mean square error as a cost function in logistic regression. Why? See here. Mean square error centers on probability, the broken standard. You can see classical linear regression uses mean squared error. When predicting probabilities, mean square error creates non-convex, judged mathematical landscape full of dead ends. Gradient descent get trapped and gradient descent confused that where is the minima for the best value of W and B. So here we use a log loss function which provide a smooth curve or smooth graph. This help gradient descent to find minima. This log loss function is like minus of y log p minus 1 minus y log of 1 minus p. Here the value of y is equals to your output, p is your probability. What is the work of this log loss function? This log loss function punished model on its bad performance. For example, measuring mathematical surprise. Punishment means how much your model will surprised when it predict. Take a real life example is that you are expecting that your friend will give you Realme phone on your birthday, and your friend will give you the iPhone. So you are very surprised positively, highly surprised. And let's say your friend give you Nokia phone, keypad, then you are still highly surprised, but in negative direction. Same way, measuring mathematical surprise of log loss function, valid confidence. Model predicts 99% this mail is spam, and actual this mail is spam. Then the system registers a tiny surprise, resulting in a microscopic loss penalty. But in the other hand, model predicts 0.1% spam and reality is spam. The system registers massive surprise. The loss penalty explodes toward the infinity. Log loss is designed to reward confidence when correct and ruthlessly punish confidence when it's wrong. Analyzing misplaced confidence, we can see the graph, loss penalty, and the prediction P with the equation this. This equation is also known as binary cross entropy. The blue line shows the positive confidence, the positive line when your probability is very nearly, when your output is nearly correct. And the red line shows the negative class when your output is nearly incorrect. This is the graph for it. The engine of continuous learning. This is same as we can say like linear regression is that here also you initialize with the specific value of w and b, then predict using this value of w and b, then cost function come, it calculates or computes the residual errors. Here we use log loss function to compute the residual error. Then we compute gradient descent. Another benefit of log loss function using is that when you use log loss function while differentiating, your gradient descent looks like p minus y into x. So first of all you predict cost function gradient update w and b, then predict cost function gradient update w and b. This cycle run until you get your minimum value of cost function or the best value of w and b. Silent failures in production environment. As we saw earlier in the linear regression also, it has many failures. Same as the logistic regression have some failures. Is that probability calibration drift. What it means? In the training data, 0.8 is equals to 80%. Means that when you train your model on data, you have cleared your data, you apply many EDA etc. on your data, so your data is clean and the model can get 80% of the accuracy. But in real world, this 80% is actually 55%. Almost these things happen. Accuracy of your training data and the testing data in real world are always differ. Training 0.8 means 80% chance. In production, it only succeeds 55% of the time. For fixing it, we should apply plate scaling or isotonic regression to recalibrate. Second player is threshold drift. In logistic regression, we have ideal threshold of 0.5. Means if your output or your prediction is greater than 0.5 means 1, and if your prediction is less than 0.5 means false. But not set as a 0.5, it's set as a point failure is extreme class imbalance. As I told you earlier, if you provide 99,000 spam and 1% normal, then it always predicts spam. Third is feature scaling entropy. Mixing widely different scale. Let's say you have the data of age and salary. Age is 20 and salary is 5 lakh. Age is 25, salary is 10 lakh. So this kind of very huge difference between 20 and 5 lakh, 10 lakh. Then just see the output. Next is expanding lodging beyond binary choice. Let's say you have to predict cat, dog, horse, bird. You have different categories and you want to predict that is if this is cat or dog or horse or bird. So how can you do that? Because in logistic regression we are using sigmoid activation function which is giving output between 0 to 1, and we are using binary cross entropy in which we get output as 0 to 1 and we have yes or no. But how can we predict cat, dog, horse, bird? We have categorical data. Then there is a concept of categorical cross entropy. What it means I will tell you later. But first, when we pass our data from a softmax activation function engine for categorical data, there is some mathematical intuition inside it and it will predict that this object has 70% chance, means 0.7% chance that it has cat, 0.2% chance of dog, 0.08% chance of horse, 0.02% chance of bird. And output will be the greatest probability. Here the greatest probability is 0.7 and our model will predict cat. See the explanation. Binary logistic regression handles purely 0 or 1. For multiple categories, we upgrade to softmax multinomial regression. The mathematics of conscious is you can see the formula. The mechanism is that the algorithm calculates a separate linear score for every class, differentiate them to guarantee positive value, and voluntarily normalize them so that all probabilities perfectly sum to 1. This is how we can work on the different categorical data also. A single neuron is a logistic regression model. Let's say you input x. In logistic regression, summation of your all wx plus b convert into S set using sigmoid activation function and you get the output. It is the single thing for remembering logistic regression very easily for concept understanding or quick revision. Every component of logistic regression maps exactly to the anatomy of artificial neuron. The input, the linear sum, the non-linear activation, and the output probability are mechanically identical. The blueprint of modern artificial intelligence. In modern artificial intelligence, you have you can see initially there are four inputs connected with a neuron wx plus b summation. It convert it into S shape. Then it further go, it convert into more tilted S shape. But it really looks like this kind of hidden layer, transformers, and billions of parameters are used to give a single output. Here you can see the components of logistic regression and its role in LLM. Sigmoid activation function. It's a neural activation function. Log loss, cross entropy loss training. Logits means linear score y is equals to wx plus b is transformer output layer. Softmax regression means next token prediction in GPT. Almost every modern AI system relies entirely on this sequence: input, linear score, activation, probability, cross entropy loss, gradient descent, and repeat this cycle again and again. The only difference is scale. Logistic regression uses on linear layer and LLM uses billions of linear layers. This is all about logistic regression. Your homework is go to the ChatGPT, learn from notes, see again video, then go to the ChatGPT, tell ChatGPT that I have knowledge of logistic regression, this. Give me a project, it probably give you the customer churn prediction project. Make this project using GPT, tell it to teach you how to write code, because as I told you starting of the video, 90% of the code in today's era AI can write them. So writing code or using AI you can make much more better than you alone do. But the concept clarity and which model you should predict and which model you should choose from your given data, which are the problems companies facing or company needs the people who know AI from core. It's for that you must know the core concept, why any model invented, the assumption, the failure of the model, the replacement of the model, when to use model, some mathematical intuition behind the model. This whole thing I have covered in this video. So meet in the next video. Goodbye.